start recording and also to get the Discord going because we got a student on the other side. All right, so I got everything up and running as far as I could tell. All right, so let me get back to this class. Are there any questions up to this point? Because at this point we have talked about several of the key components. One is resolution, two is CNF, conjunctive normal form, three is proof by contradiction. So what we'll do today is to do some actual proving. All right, so today we're going to tie all of those things together. Yes?
Can you show how the resolution helps with algorithm termination?
When we get to that. Yeah, because the idea of applying resolution is so that we can conclude whether a proposed theorem is a theorem or not. Yep. But basically, every time you apply resolution, you are creating a new expression that has one fewer variables in it. So that means if you just quote unquote infinitely apply resolution, at some point you'll get nothing left. Is that okay?
And the alternative to not doing resolution, can you still get the answer? Like, why is the alternative lengthy? Like,
Yeah, so resolution is one way to prove a theorem, or it's one link in the entire chain to prove a theorem, and to do it mechanically. So the alternative is not to do it mechanically, which is to do it manually. So to do it manually means you have to go through the same process as in pre-calculus or in algebra, where you're going to have to go through the process of, okay, what rule do I use next to transform the expression so that eventually, hopefully, we'll get to the expression that we want it to be. But resolution is nice because it is very mechanical. It's actually very easy to program. Even at this point right now, with CISP430, code as a code requisite, and CISP400 as a prerequisite, you guys can actually write this program, just not in a week, in a week's time. Some of you can probably do that in a week's time, depending on which programming language you want to use. I think in C++ it's going to take a little bit longer, but in most scripting languages like Node or Python, it would actually take less time because symbolic processing is a little bit more. It's easier to express in those other languages compared to C and C++. C and C++ can do a lot of fantastic stuff, but symbolic processing is not one of its the best thing it can do. Um, so so I will make sure that I address that question in today's class. All right, so we're going to go through a few examples, which is also in the module. So that means I really hope everybody has a chance to read the material as we go, because this way you basically can track where we are at easily and be able to follow along in the lecture. I'm still grading the exam, so that's I was hoping that I had more time to do it. I finished up the other two classes that I had to grade, so this one is basically the last one, and I'm still in the process of doing it. All right, so any questions about the CNF assignment? The conjunctive normal form assignment, are there any questions about that one? It is due next Monday, so you still got a weekend to do it. But if you have started and you have some questions, you got stuck somewhere, today is a good day to ask those questions. If not, we're going to go back to propositional logic, and this time we're going to look at an example. So there we go. So we got an exercise, and what we have here is the first thing we need to do is to convert it into a well-formed formula. This is well-formed already. We want to convert it into a CNF or a conjunctive normal form. Obviously, this is already done down here. Nope, this is proved by contradiction. So I'm going to work with this one, and we'll see how to convert it into CNF. Let me see what is the example that I use later, because I want to make sure that we're going to do the same thing. Yep, we're going to use the same, continue with our example above, and the given is expressed as follows. And okay, we'll work with this one. All right. All right, so do you guys remember last time, we have a mechanical method to turn this into a CNF by using a truth table, look up all the rows that are zeros. That will give us, all the disjunctive elements, all the DEs, and then by making a conjunction of all the DEs, then we can accomplish the same thing. So instead of doing that, I'm going to use linear algebra. Okay, so I'll go ahead and use linear algebra to solve this one. So let me get rid of the tab and use just a text editor for this demonstration. Mouse pad, there we go. All right. All right, so we are going to start with not P or not R implies Q and P or T. So that's basically a quick translation from the conventional math notation to the shorthand that I prefer to use in this class, just so that I don't have to type ampersand as and then bar as or. So it's just a lot easier for me to type using the shorthand. Is that okay? Does everybody understand that this is just a shorthand? We are not really talking about multiplication and addition. We are really talking about the Boolean operators. Okay, very good. So now we want to convert it into a CNF. As usual, the first thing that I do is to get rid of the implication. So I will keep everything else the same, but I turn the implication to the negation of the left-hand side, or the unnegated right-hand side, sorry. Negate the left-hand side and leave the right-hand side alone. There we go. So we're actually kind of close already. So the next step, okay, can someone tell me, according to what I have done so far in this class, what do you think is going to be my next step? What is my favorite thing to do? Or, I want to get all of those things done before I do anything else. De Morgan's law. Move all the negation onto the variables, okay? Because we can see there is a negation here, right here. This negation is applied to the or over here. I don't like those, so I'm going to use De Morgan's law to move that in so that the negation is moving onto the components of the or. So now we end up with not R as one component. Let me put parentheses around it first. And then we have not Q as the other component. But the or becomes an and. When you apply De Morgan's law, and becomes or becomes and. So that's what we end up with. So this entire thing, this part here, ends up being like this. It is just a conjunction. And because we have a conjunction with P or T, and according to the associative law of conjunction, we don't need extra parentheses. So are there any questions about this particular derivation, how we arrived onto the third line of this expression? Yep.
Why does the initial negation not affect P or T?
The original negation.
Isn't it
Which negation are we talking about?
The first not P, right?
The first not P? Yeah, not P is entirely outside.
not the not P, within the parentheses?
Within the parentheses.
Like before.
You mean this? Okay, so negation applies only to whatever is immediately to its right-hand side. So this negation applies only to this. And it does not apply to that. Because there's okay, so if you look at asterisk as and, so this and here has a lower priority compared to the negation here. So the negation is immediate. It applies to whatever is on the right-hand side, which is just this disjunction. Okay, that's a good question. It has to do with operator priority. So to make it more clear, I could use an extra pair of parentheses like so. So now it becomes a little bit more clear. And I will put the extra parentheses here as well. There we go. So does that make it more clear? Okay, all right. All right, so at this point, I can do some simplification, just because this one is kind of nasty to look at. So not R is just R, not Q, well, I mean, it's just not Q, and then P or T is P or T, like that. So if I really want to go for the simplest way to express this, I could go in this route. But on the other hand, if we want to make it clear about the operator priority, I can put parentheses around the not Q. So this way we understand that the negation is applied only to Q, but not to P or T. Is that okay? All right. All right. So at this point, I have a OR as the last operation. This OR here is my last operation because it is a disjunction of the left-hand side and the right-hand side. And obviously, this is not in CNF yet, right? Because CNF will end up with an AND as the overall operation. So the question is, what am I going to do at this point? Mm-hmm.
I see a P and not P.
Sorry?
If there's a P and not P, then doesn't that cancel them out?
But we are not applying resolution yet. We are just using normal Boolean algebra. So I'm going to use distribution. Yep, go ahead. Sorry. Okay, so you're planning to use distribution?
Yeah, on the P and the junction and apply to R not Q and P T.
Say that one more time. Sorry.
So the not P in the disjunction, you distribute it to.
Yep. We will distribute to all three. Yep. So let me rewrite, basically write out the basic um, rule of distribution. So in this case, we have A plus BC. Okay, BC. Actually, we have three components. We have BCD. So in Boolean algebra, this can be rewritten as A plus B, or A or B, and A or C, and A or D. That is a unique rule of distribution that only applies to Boolean algebra and not applicable to your usual algebra. But this one is super handy, right? Because now, just because of the form, I think we are pretty close to getting everything done. So, so once we know the rule, it is now time to associate, okay, what is A? A is our not P. What about B? B is our R. C is our not Q. And then D is a little bit interesting. D is not a single thing. D is actually a disjunction between P and T. But that's going to be fine because the way we are going to use D is to say A or D. So if D is already a disjunction of terms, then A or D is also going to be a disjunction of terms. So I think we got everything figured out at this point. So we'll go ahead and just do the actual distribution. So we got not P or not P or R, and not P or not Q, and then finally we have not P or T. That's what we are going to end up with. And then at this point, I'm going to do some simplification because I can see that we have the negation of P and P also in the same disjunction. So between these two, okay, if I just focus on between these two, one of them has to be true because they are negations of each other. So if one is true, the other one has to be false. As a result, if I look at just this particular disjunction, it is true. So that means if I want to go really step by step, I can now say this simplifies to just true. But then when you have a true in a disjunction, regardless of what else is in the disjunction, the whole thing is going to be true because you can only be, once you have true, true or whatever is going to be true. So this part here is actually useless. It does not add anything to it. And as a result, we end up with this. But then you end up with a conjunction that has true as one of the components. True is what we know as the identity of conjunction. which is kind of like 1 times 5 is 5, 1 times 10 is 10. So in this case, this true is doing the same thing. It is just the identity. You can AND true all you want. It doesn't change the original expression. So we can now also simplify that one out of the whole thing. And now we end up with not P or R and not P or not Q. Now, is that right? I mean, how do we check that this is right? There are a few ways to check. One is kind of go back to the process, to the steps, and make sure that we actually carry out all the steps correctly. That's one way to do it. Two is to make truth tables, right? Make a single truth table, evaluate the first expression, make its own column, and then evaluate the final form, which is what we call the CNF, and make sure that on every single row, the two expressions end up with exactly the same value. Yep.
You see how there's a not P in both of them? And how in the one we were able to distribute the not P or? Could we just do that opposite and take it out of both of them? And have it so it's not P or R and not Q?
Say that one more time.
So do you know how we distributed not P over not Q and P or T on the fourth row?
Tell me which row we are on.
On the fourth row.
This one?
Or one above it.
Okay.
That one.
Uh-huh.
Now we distributed the not P.
We can distribute the not P.
Like that's what we did, right?
That's what we did.
Yeah, so couldn't we do the opposite of that at the very end and simplify?
At the very end.
So the last one, so there's kind of the pattern, right? Can I write it on like the void? Would that be easy?
Can we factor out not P?
Can we factor out the not P?
Yeah.
How do you factor out the not P?
Because it's kind of like the same pattern. Can I write it? Would that be better?
Yeah, go ahead.
So like, there was A
Mm-hmm.
and B, C.
Mm-hmm.
So obviously then it's just A plus B, A plus C.
Mm-hmm.
So couldn't you just reverse that process for that right there? So obviously it's not P or R, or not P or Q. Yeah, or not Q. So couldn't this potentially just be not P or R, not Q?
Okay, now I see what you mean. Okay, very good.
Does that make sense?
So in terms of Boolean algebra, it is correct. So let me just write it on the screen, just so that we can see it here, and also that it is going to be visible to the person who's online. So yes, so the answer is yes, we can do one more factoring and extract the P out because it is common, and then the other side just have R, and not Q. The answer is yes, we can certainly do that. The question is, did we end up with a CNF? That one extra step does simplify the expressions, but we end up with something that is not a conjunctive normal form anymore. This is a disjunctive normal form because overall we have a disjunction, and then each item that we are ORing together is a conjunction. So it is not exactly what we need in order to carry out resolution. Yep. So you're correct. From the Boolean algebra perspective, you can take it one more step to simplify. Yes. But from the perspective of what we actually need, which is a conjunctive normal form, that one extra step breaks it. It's no longer in conjunctive normal form. Yep. Mm-hmm. All right. So even though this is correct, we cannot use it. That's kind of the deal. All right. So are we okay so far with this derivation? All right. And once again, we have how many terms? We have 1, 2, 3, 4 terms in this case. So if I were to make a truth table out of this, it's going to have 16 rows to that truth table. And you would probably want to have a mechanical method to do it. So over the years, okay, because I have to grade exams and stuff like that, I have written stuff to help me. I can copy and paste these expressions, slap it into the script, and it will generate the truth table for me. So I basically wrote my parser to parse the infix notation and kind of crank out, so now I can basically regenerate the equation in any form I want. So that's something that some of you may learn in a 4-year university in a class usually called compiler design. Then you will learn how to write parsers that can parse infix notations. Infix notation, by the way, which is what we are used to, putting the operator between the two values that we operate on, turns out to be much harder to parse compared to the prefix notation and also the postfix notation. The prefix notation needs a lot of parentheses, but from the parsing perspective, it is easy. It's just like that, okay? The postfix notation is almost like, oh, that's nothing to parse, okay? The infix notation, which is what we are taught to use from childhood, is the worst of the 3 form to parse. So a lot of things that we are taught, in elementary school, such as infix notation and base 10, they are they are some of the worst possible choices. If I were a politician and I want to reform, I'm going to reform those 2 items first. It's like, let's teach binary numbers instead of decimal numbers, and then we'll use postfix notation instead of infix notation. I don't think I'm cut out to be a politician.
Yeah, good luck with that. We're still using imperial units.
I can have a tiny little country with only nerds and geeks, and I'll be the king. No, I'm not. Because there are a lot more people who are smarter than I am, so I cannot be a king in that country either. But I can at least propose all of these things. That makes our life a whole lot easier. Okay, so now I want to propose a theorem. This is a proposed theorem right here. So the proposed theorem is, okay, ignoring this part, it is simply saying not T implies P. Okay, I want to know whether this statement here is implied by psi. So once again, let me point out what is psi. Psi is this part here, which is something that we just converted from a regular well-formed formula into conjunctive normal form. And then this is my proposed theorem. The proposed theorem is simply not T implies P. So what I want to know is to ask, does psi implies phi? Are we doing okay so far in the concept of what is a proof, which component is what you're given with, and which component is the proposed statement or the proposed theorem that we want to see whether it is implied by the other one or not? Are we doing okay so far with those terms and the structure of what we are trying to deal with here? Maybe. Do we need more explanation or nope? Okay. All right. So we are going to move forward, but I do want to make this really clear. Okay. So the question is, okay, I'm just going to copy this thing here because I really, really want to be extra clear of what we are trying to do here. We're asking, does that imply, I'm going to stash a question mark on top of that to emphasize that we do not know, but this is what we want to know, is whether this implies not T implies P or not. This is the question that I want to answer. Is this implication always true? Now, you can almost always find cases where that implication is true, but what I'm asking is, regardless of the values of P, Q, R, T, is this implication always going to be true? That's what I'm asking, okay? So the technique to do this is once we have the CNF corresponding to psi, now we want the CNF corresponding to phi, but not just phi, but a negated phi. So we look at phi, which in this case is not T implies P, but phi itself, I don't want to convert phi into a CNF. I want to convert not phi into a CNF. That has to do with proof by contradiction. I hope you still remember the proof by contradiction example from Monday, as well as last week sometime. You have to negate the theorem that you want to prove, and then you say, if I just kind of put this into a conjunction with everything that is known to be true, do I end up with a contradiction, which is basically a fancy term of false? That is what I want, okay? So now I want to say, so I want to convert not phi into a CNF. So we'll go ahead and take a look at not phi in its original form. And now we will do the conversion. So my convention is to change the implication to a or. So we have to do a negation on the left-hand side or the right-hand side. And obviously this is easy to simplify. And now I can apply De Morgan's law. So I can distribute the negation to the inside. So now I end up with not T and not P, which is already in CNF. We do okay. Does everybody understand why not T and not P is in conjunctive normal form already? Now, if anyone is arguing, go like, I don't see the DEs. In other words, I don't see not T being a disjunction element. I can fix that really easily. Okay, just watch me. All right, well, there's your disjunction. Happy? Because anything or false is just that anything. In other words, 0 in arithmetic is the identity of addition. So as it turns out, false, which is also represented by 0 in this notation, is also the identity of disjunction, which I borrow the plus sign from arithmetics. Are we good so far? All right. So now we look at this. I'm going to get rid of these first. So now what I need to do is to say, because remember, the ultimate question that I'm really asking is psi and not phi. I want to see if this is false or not. I want it to be false because if this conjunction turns out to be false, that means phi is a theorem, which also means it is implied by psi. Are we okay so far? All right. So this is where I use resolution. So hopefully this is going to address the original question of, okay, what do you mean by, now we know how much time it takes to get to a dead end. Okay, so we'll go ahead and do this first, and then we'll basically theorize and ask and make the claim that even for something more complicated, it will only take finite time to get to a conclusion of some kind. All right, so we look at psi. Now we look at psi, this was what psi looked like, but since we can derive it to become this CNF, that is also psi, okay? It is equivalent to the original expression, so that's where we're going to start first, okay? So we will copy this particular CNF, which is kind of like an alternative form of expressing psi, and then we look at not phi. Okay, this is not phi because it is the negation of what phi is, and then we convert it into a CNF eventually. So that means now I take this as not phi, and we form a longer CNF. Now this CNF is no longer psi. It is not phi either. It is a conjunction of those two. So the objective, what I want to be able to do, is to conclusively say whether this is false or not. Are we good so far? So this is where we apply resolution. So the way we look at this is we ask, between the terms in the conjunction, can we find a variable that is not negated in one and the same variable is negated on the other side? As it turns out, we are at a dead end already. There's no way to apply resolution in this case because if you look at, so we can do this very systematically, okay? So let me try to explain the systematic way of doing this. We start with the first expression, and then we try to pair up the first expression with the second. And we ask, is there a variable that is negated on one side but not negated on the other side? Well, we only have 4 variables here, right? We can just count each one and see if they work. So P is negated on one side, it's also negated on the other side. Not a good candidate. And it doesn't have non-negative p on the other side. So let's look at r. R is found on one side, but it's completely missing on the other side. So I'm still missing the negation of r on the other side. And that's the conclusion. The first and the second expressions cannot resolve. Let's look at the first and the third. Okay, it's not going to work because the variables don't even match up. The 2 on one side is missing on the other side. The 1 that is on the other side is missing on the first side. So it's not going to work. So we look at the first and the fourth. Well, it's not going to work either because they both only have not p. R is missing on the other side, so it's not going to resolve either. So at this point, I already come to a conclusion that this cannot resolve to 0. Now, there's a difference between whether it can resolve to 0 versus can this expression be false. So if the question is okay, let me highlight when I say this. If the question is whether this expression can be false, the answer is yes, it can be false, easy. All you have to do is to make p true, then this entire thing is going to be false. Or you can make t true, so negation of t is going to be false, and once you have one false in the conjunction, the whole thing is going to be false. So if the question is whether you can make it false, the answer is yeah, we can do that. But that's not the question. The question is, can you make this thing false regardless of the values of all the variables? Then the answer is no, you cannot. Are we good so far? Are there any questions about what I said? Does anyone want me to clarify what I just said? Nope. Okay. All right. So now we look at another proposed theorem because I'm too lazy to start with another psi. So we'll just be dealing with another phi. We call it phi prime. So this is phi prime, which is another proposed theorem. So this proposed theorem itself is saying P implies not Q. Okay. So I'm going to work with this one now. All right. So I'm just going to copy something over here. So phi prime is P implies not Q. So first, we have to negate the proposed theorem. So we are now looking at the negation of phi prime, which is just the negation of what we had earlier. And then we turn it into a CNF. So once again, you convert the implication first. So it becomes not P or not Q. And then we apply De Morgan's law, which means we end up with not P and not Q. And then we do one more step of simplification. So we just end up with P and Q. Are we doing okay so far with this?
So for the previous one, it's just undetermined at this point?
Nope. The conclusion that we draw here is it is not a theorem. So as a conclusion, because we cannot resolve to 0, phi is not a theorem, which also means psi does not imply phi. Is that okay? Yep.
So in order for the for phi to be a theorem, the CNF has to be 0 regardless of the.
It has to resolve to 0.
Okay.
Yep. But in this case, you can't even do one single step of resolution, let alone resolving it all the way to 0. All right. Any other questions? These are all very good questions because I would much rather have a discussion to get the concepts clarified as we talk about it than to utilize the concept and then later on we encounter some issues because of the lack of clarification. And that's why I really like in-person classes because we can do this. With an online, especially asynchronous class, that becomes really hard to do. Not impossible, just much harder. So are we good so far with the concepts? All right, okay. So now we do the same thing. So now we want to combine psi, which is everything that is given to you to be true. You can look at psi as a conjunction of everything in iota. Do you guys still remember iota? one of the components of a propositional logic system. That's basically what psi is. It is a conjunction of all the expressions in iota. Everything that is known to be true to begin with. Okay? So now we want to take an and here. So we want to look at this and phi prime. Phi prime is basically one of the well-formed formulae, or corresponding to one of the well-formed formulae in the entire space of well-formed formulae. And we just want to say, if we just use all the productions or the transformation rules, can we eventually infer that phi prime, not the negation thereof, can we infer that phi prime is also true as a result of iota? So what is this negation doing here? It's because we are proving by contradiction. So when you use proof by contradiction, you negate the theorem that you are trying to prove. And then you combine it using a conjunction with everything else that is given to you. Is that okay? All right. So now we look at this and here. I'm going to just do the lazy thing of copying and pasting. So I will copy from here. This is psi. And then not phi prime is just this. Okay. So we'll look at, this is what I call it super CNF because it's the conjunction of two CNFs. So it is just a longer CNF. So I want to see if this is false. Okay. Can we come to the conclusion that this is false regardless of the values of P, Q, and R in this case? Okay. T is gone entirely, I think. Yeah, T is entirely gone. Okay. All right. So let's do some resolution. So the same procedure, okay, the same steps. I try to do it more systematically. You guys do not need to. Okay, so in an exam, if you just go like, oh, I can eyeball this whole thing and find the quickest way to get to 0, that's fine. Okay, but I prefer to do things in a more systematic way because once you figure out a systematic way to do something, you can write a program to do it. Okay, you cannot write a C program and say, I refer to the eyeball algorithm. Try that in 430 or try that with one of your programming classes and just tell your professor in the comment of a section of code, it's like, I'm applying the eyeball algorithm here, and therefore the answer is going to be right. That is not unlikely to work. And it is almost certainly not going to work when you're actually working and someone's paying you to get a program developed, and then you just turn in a program with a comment of, the eyeball algorithm is here, and therefore the algorithm, this function is going to do the right thing. That is not going to work for sure. Okay, so systematic. Look at the first one, look at the second one. Not much we can do, okay? If we see not P on one side, we want to see P on the other side. Not happening. If we see R on one side, we want to see not R on the other side. Also not happening. We look at the first one and the third one. We go like, that can work. We have not P on one side and only P on the other side. But then you go like, but then what is the result of this, right? Because we have P, NP, and then we have not P, and then we have P. So after we do the resolution, what is left? Remember, resolution is kind of like concatenation, except you remove the variable that is acting as a bridge. So in this case, variable P is acting as a bridge, so it doesn't appear in the result of the resolution, but everything else is going to be concatenated, okay? So let me just kind of use a notation to indicate what we are picking to perform the resolution. This is the first one, this is the second one. So now the question is, what is the result of that resolution? Yep, just R by itself. You're correct. So now I can now say my CNF just got a little bit longer because the result of resolution can be appended to the entire conjunctive normal form and it still won't change the meaning of the entire thing. So I can actually just extend the length of the CNF as we perform resolution. And why is that the case? There has to be a reason why we can say once we apply resolution, the result of the resolution can be appended to the conjunction without changing the value of the conjunction itself. And the question is, why is that the case?
They should be the same, yeah?
Well, whatever
Or
the
they should
result,
have the same result.
it's implied by, right? The result is implied by some of the expressions in the original thing. So the question really boils down to, if you have a conjunction and then you have something that is implied by the conjunction, can you and that thing that is implied by the conjunction to the original conjunction and not change the meaning of the conjunction? Okay, let me try to write it out, because I think it's harder to say it. It's easier to express it like this. Okay, so what we are saying is, let's say A is a placeholder for something, B is the placeholder for something else. So AB is a conjunction between those two. So we're given the AB, and then we also know for sure that AB is implying C. So right now I'm using some really abstract terms here. A is some kind of expression, we don't know what it is. There's also B, which is a placeholder, and we only know that AB as a conjunction implies C. The question is AB the same thing as ABC? That is the question. Regardless of the actual value of A, B, or C, are they the same? Is AB the same thing as ABC when C is being implied by AB? All right. What is the tool that we have learned to use in this class? Truth table, right? So let's do it with a truth table. This one does have a twist, okay? This one has a twist to it. So it's not quite as plain as a truth table that we are used to. So let me first generate the truth table first. I really should write a program to do this so I don't have to do it by hand. I mean, it really is just the binary numbers corresponding to 0 to 7 in this case. Another reason to use binary numbers instead of base 10 numbers. All right, so now we have A, B, C as independent variables, except they are not really independent, are they? Because we know that C is implied by AB. So some of these rows do not apply. Okay, so we have to spot the rows that do not apply and get rid of those rows first. All right, so can someone tell me which rows do not apply? Okay, we'll just go through each one, one by one. Is that okay? In other words, if A and B are both false, false and false implies false. Okay, that seems okay. False and false implies true. Is that okay? Seems okay. Well, that's going to be okay because the conjunction between anything that has a false in it is going to be false. False implies whatever is always true. So we know these two are going to be okay. These are the ones that these two are the ones that I have concern about, because these are the two where both A and B are true. So that means we have the left-hand side of an implication being true. So that means we need to be careful, because if the left-hand side is false, which is all of the other cases, we got nothing to worry about. It's only when the left-hand side is true that we have to be careful. This row here, 1, 1, 0, is the one that does not apply. Okay, this one does not apply because when A and B are both true, then A and B is true. Then we have true implies false in this case. That is not good for the implication. The implication is going to be false. But since we are already told that this implication is true regardless of the values of A and B, so that means this row does not apply. We have to get rid of this row. So I'm just going to put an X, here, or put asterisks here, to basically say this row cannot apply. We basically have to ignore this particular row. All right, so with all that said, now we have to look at AB and ABC. So we look at AB and ABC, and then try to figure out the value of these two conjunctions. given the values of A, B, C like this. Okay, I just misaligned my header. Okay, that's better. All right, so if A and B are both false, yeah, that's false and that is false. If AB is false, ABC is false. Okay, that seems fine. Yep, yep, okay. This is also okay. This is also okay. This is also okay. And then we look at the last one. Yeah, it's okay too. Because in this case, A and B is true. So is A, B, and C. So other than the row that we said earlier, and go like, no, no, we need to ignore that row because C really is not independent of A and B. C is implied by A and B. And this one says the implication is false. So we have to ignore that row. So for all of the other rows, you can see AB versus ABC, they gave us exactly the same result. So this is the proof, okay, that if you are told that this implication is true, A and B implies C, then AB really is the same thing as ABC. You can also work it the other way around, which means you can start with ABC, but if one of the components can be implied by the other components, you can simplify the component that is implied out of it. So that's also a tricky thing that you can do with Boolean algebra, is to remove terms that can be implied by the other terms. But that's not the direction we're heading. We are basically appending more and more quote unquote useless things, okay? And the reason why we are appending the quote unquote useless things is because that will give us more things to resolve with, okay? And hopefully one of these resolutions will get us the thing that we want. All right, so we look at this form here and we ask, can the first expression resolve any further with the other terms? So we look at this and then we look at the fourth term and go like, nope, cannot resolve because one is only referring to P and R, the other one is only referring to Q. They don't even share a variable in common. No resolution between those two. Then we look at the first one and the last one, okay? That R was the result of an earlier resolution, but we can resolve with that one too. So everything in the conjunction, whether it was from the original quote unquote super CNF or it is a result implied by other steps of the resolution, they can all be used in resolution. Okay? But it's not going to work because even though the first term has a R, the last term also has just a R. If it had a not R, then we can resolve. But since it only has a R, it cannot resolve. So no dice here. So now we have to move on to the second one and try to pair that up with the third and so on. So you can see this is a really, really systematic way of looking at things. In other words, I'm basically just using a double loop. The first loop, just go forward with one index. The second loop starts with the index right after the first index and then move to the end. So this is a double loop, very, very systematic. The order of magnitude is going to be big O of n squared, where n is the number of things in the CNF. Okay? All right, so we look at the second one and we look at the third one and you go like, that resolves, right? Okay, so let me do the pseudo underline between those two. See, these two can resolve because one has the negation of P and the other one has P not negated. Yeah, we can resolve. All right, so when we resolve that, we end up with just not Q, I think. Yep, we end up with just not Q. So Q becomes an additional term to the entire CNF without changing the value of the CNF itself. So some of you can see, oh, there's a negation of Q. So some of you can see right away, it's like, oh, we're done here. But remember, I'm going for the really, really boring and systematic way of doing things. So I don't see the answer just yet, okay? So we look at this, and then we still are looking at the second term. So we are still looking at this term here and ask, can we resolve this with Q? The answer is, yeah, we can do that. So we'll go ahead and resolve it with, oops, I just pressed the wrong key, with this Q here. So yes, some of you are already realizing that I'm just wasting time. In other words, I'm wasting your tuition of $40 per unit. And now we say, okay, we end up with a not P here. There we go. And I'm not done yet with all the boring stuff. We're still looking at the second one and see if we can resolve with R. Nope, cannot resolve with R. And then not Q came out of this one, so obviously cannot resolve with not Q, and also cannot resolve with not P. Okay, so we are done. We are completely done, like 100% done with the second item in the conjunction. So now we can move on to the third one and do it in a very systematic way. So we look at this thing here and we ask, can it resolve with the next one, which is Q? The answer is no. Can it resolve with R? Nope. Can it resolve with not Q? Nope. Can it resolve with not P? Yes. So this is the one thing that you go like, we're trying to do a concatenation and remove the bridge thing. So what are we left with?
Zero.
Zero, exactly. Because every single one of these expressions has, you can basically say every single one of these has an implicit this in it, right? Because you can do this all day long, it doesn't change the meaning of the expression at all. So we'll go ahead and make it more explicit this time. And then we say these two DEs, or disjunctive elements, can indeed resolve because one has P and the other one has not P. So when it is resolved, then we have a concatenation of the entire thing, which only has 0 or 0 left. Is that okay? Does everybody understand how I wound up with 0 or 0 in the end? Okay, so what is the big deal? Okay, it looks like a bunch of syntactic manipulation, which it is. Okay, this is the whole point of using resolution and CNF, is it is completely syntactic. You're just matching. Do I have a not something on this side and a not and a non-negated thing on the other side? That is easy to do, right? It's just symbolic processing. So now we can. Okay, so I just want to simplify this. Would anyone argue and say 0 false or false is really not false? I don't think I will see any disagreement here. All right. So now we end up with a false in a long chain of conjunction. It is still a conjunction. So what does that mean to the entire conjunction itself?
False.
It is false. Okay. So the conclusion is this entire thing is false. But where did we start? We started the whole thing with the negation of the theorem that we want to prove and everything that was known to be true, that was given to be true. So according to proof by contradiction, the fact that we end up with a false means the theorem is, okay, so this is the important part. The theorem is not true. The theorem is simply implied by everything that is known to be true, or everything that is given to you as true to begin with. Is that okay? So the conclusion now is to say, because the resolution ends with false, phi prime is a theorem, or you can say phi prime is implied by psi. That is the conclusion. So are we doing okay so far with what resolution is and how to utilize resolution in conjunction with CNF, in conjunction with proof by contradiction, to actually prove whether a statement is true or not, or whether a statement is implied by everything that is given to you as true. Yep.
Is phi prime now in iota?
Sorry.
Is phi prime, can it be included in iota?
It doesn't get included in iota because iota by definition is everything that is, it has to be finite. It's just whatever you're given with. So we are not expanding iota. we are indeed expanding something. Okay, so does anyone remember the name of the set representing everything that can be implied to be true? That was like 2 weeks ago.
D.
Hmm?
I said D.
Set D, exactly. So you can add this phi prime to D now, but not to iota, because iota is set, it's basically finite and is given to you, so you cannot change it. You can look at iota as one of the input parameters. That's a const. So you're not supposed to change it. But you can add it to D, because after all, the way we define D is everything that can be implied by the stuff in iota. All right, that's a very good question. And I'm actually impressed that you remember the set D from that discussion. All right, so any questions about what we just did by hand? Even though I try to do it as mechanically as possible, it is still done by hand. So are there any questions about that portion? No questions? Okay. So if I were to ask you, okay, this is just hypothetical, don't sweat just yet. If I were to ask you to write a program to prove theorems, okay, I will give you the iota set, and I'll give you a particular theorem like phi and phi prime here, and I ask you to prove, one way or the other, whether the proposed theorem is implied by psi or not, or everything in iota or not, how would you go about doing it? Well, first of all, are we going to encounter the problem of trying to find a needle in a haystack that is infinitely large? The question is, what haystack are we talking about? The haystack that we are talking about is how many different types of DEs can you end up with. This is one DE, a disjunctive element. This is another DE, another DE, another DE, another DE, and so on. So let's just say that we have 5 variables. How many possible DEs can I end up with? So we'll try to address that question first. Okay? 5 variables, P, Q, R, S, T. And we are looking at the number of possible DEs. So in each DE, disjunctive element, you can have a disjunction of any combination of variable that is non-negated or the negated version of the variable. But each variable can only appear once, whether it's negated or not, it can only appear up to once within a DE. So those are the requirements. Okay? The easiest way to look at this, okay, let me take row first, because I haven't taken row in this class for some time, so I just felt like maybe it's time to take row again. And we'll go ahead and find one of these. Okay, I'm gonna pick up. We'll pick this one. And this morning I made a stupid mistake in my class, and today's the 12th. Yep. I forgot to update the question, even though I was trying to use a different way of collecting the row. So you guys can sign in first. It's going to take me a little bit of time to set this up. So we'll go like CNF is the access code. I'll write it on the board. So you guys can just sign into Canvas at this point and give me a little bit of time to set up the question, because I'm going to change the question to something that's a lot easier and makes more sense. Okay. Oh, this is great. By the way, I use a language tool as a plugin, and it helps me fix all kinds of problems. So let me let me do that again here. Oh, okay, it actually checks out everything. So when I select the word, it would tell me more about the word, which is helpful. But if I use bad grammar, let me show you what bad grammar is in this case. So I would say me present in class today. Okay. Uh-oh, it doesn't complain about it. Okay, let's try use more bad tense here. Okay, now it says it's bad. I Okay. That's okay because syntactically it is correct because this can be interpreted as I present today. I present in class today. So let's find out all the ways where the grammar is actually technically correct, but it is actually wrong. Because I is singular, right? And is also singular. So in theory, that should work, except we are talking about English here. Okay, I am sorry. I was just having too much of a good time with language tool. But it's it really is great. I mean, it will spot little things like, oh, you're supposed to have a comma over here, or you're supposed to use a semicolon here and stuff like that. Yeah, and it's really quite good. Okay, so if you refresh right now, you can go into the so-called quiz. Yeah, I did save the question this time. So if you use CNF to get in as the access code, then you can just say true, yes, I am present in class today, and then submit, and you should be okay. Is that what you guys are seeing, or did I forget to update the question? I forgot to update the question again. Yeah, I think I did update. Okay. Because earlier in my CISP440 class, I forgot to update the question. Canvas does not warn you when you forget to update the question and you click save. It will just save it as if you updated the question, but it actually did not. Anyway. All right. So getting back to this stuff here. All right. So getting back to this stuff here. The question was, if I give you 5 variables, P, Q, R, S, T, can you give me the total number of possible DEs? How would you figure out that number? Well, first of all, is it going to be finite?
Yes.
It has to be finite, right? It has to be something to the power of 5. The question is what to the power of 5? It's not 2 to the power of 5 because I think 2 is a very logical guess because, well, it's either the variable or negated. But you're forgetting that it can be completely missing. So we have 3 choices for each variable. So it's 3 to the power of 5. So with 5 variables, you have 273 possible Ds. That's the total number. Okay? So it doesn't matter how much you apply resolution, you cannot exceed that upper bound. 273 is your upper bound. You cannot exceed it. So right here, we know that the haystack is finite. Now, what about the resolution? Well, you can see the way I apply the resolution is very systematic. It's a double loop. It has to end at some point. It cannot go on forever and forever. It doesn't oscillate. It does not generate some terms that are just getting longer and longer but meaningless otherwise. So it has to end at some point. So we know the upper bound of this algorithm is going to be 3 to the power of the number of variables. Now, is that a good algorithm? No, it's not a good algorithm. But at the same time, it does give you an upper bound. The haystack is finite. You can basically go through the entire haystack and just say, nope, the needle is not there. Is that okay? As opposed to the other way, where the haystack is infinitely large. So it would be very difficult to come to a conclusion of, well, I cannot find the needle just yet. Okay, I spent 4 years, 6 months, and 17 days. I still haven't found the needle, but I cannot conclude the needle is not there because the haystack itself is infinitely large. So I cannot guarantee the rest of the haystack that I have not explored yet does not have the needle. In this case, it might take a long time. If you have like 20 variables, it might take a little bit of time, but you know that at some point it has to conclude. Is that okay? Now, I know writing this kind of program may be new to many of you, but the thing is, do you get the sense that this is very, very systematic? So it's a matter of time to implement it. There's no black magic involved in something like this. Do you guys know what I mean by when I said black magic in coding? There are a lot of things with black magic. Compiler optimization used to contain black magic in it. When you have logic specified in a HDL or hardware description language, and you want to compile it to silicon to make a processor to actually make something that you can make a die out of, that contains black magic too. So they have heuristic rules of thumbs that apply, and you can tweak the threshold when to apply something and when not to apply something. So there are 20 bazillion dials, to those tools to control the black magic. This is not one of those things. This is like easy from the perspective of ways to optimize and things to get it to work. This is straightforward. All right, so that is the conclusion of the propositional logic module. Do we have any questions? Okay, if you don't have any questions, we still have 10 more minutes. I don't want to squander your tuition fees, so I'm going to keep going for another 10 minutes. So I'll give you guys a choice, okay? You can choose how to proceed at this point. I can give you several things that we can proceed to. So let me just use the mouse pad here. Okay, so I'll give you the options, okay? One option is Prologue, which is Predicate Calculus. It's kind of like theorem proofing stuff, but except this time we got quantifiers in it. So think about propositional logic stuff, but with quantifiers thrown into it, okay? So that's Predicate Calculus, which can be done in Prologue. Prologue is an actual programming language. So it can actually do stuff for you. And it's kind of fun to write programs in Prologue in a certain way. Most people hate it, but I find it to be quite interesting. So that's one way to proceed. Another way to proceed is to look at, talk about combinatorics. So combinatorics, the best way I can describe it is one application is what are the chances that I can buy a lotto ticket today and at least get $5 out of it? Okay, that's combinatorics. Okay, you're looking at combinations, permutations, the chances of blah, blah, blah. Okay, that sort of stuff. That's combinatorics. And for the first time ever, since I have taught this class, I will even throw graph theory, not so much graph theory, but I will just go Dijkstra's algorithm, into the mix. So you can choose, Dijkstra's algorithm will eventually be presented in CISP440 that Iraj teaches. So if he has not taught it yet, okay, you can wait until he teaches it, and we can teach this topic after his introduction to Dijkstra's algorithm. I'm good either way. So I want you to kind of think about which way to proceed. Normally, I proceed with combinatorics, and then I swing back to Dijkstra's algorithm, and then to Prologue. But there's no particular right way of doing this because all of these are, except for Prologue, depending a little bit on propositional logic. The other ones, they don't really rely on propositional logic. Yes?
What's the use of Prologue again? What is the use of Prologue again?
Prologue used to be an AI programming language. So if you look it up, okay, that's a very good question. So if you look up Prologue from Wikipedia, okay, it is a programming language that once was associated with AI. So it is still associated with AI. It's just not the AI that you guys grew up to believe in, which is strong AI, which is imitating how people do things. This belongs to weak AI, which is programmatically or using algorithms to solve certain problems that people used to think only people can solve. So it can basically deal with logic. Okay, the best way to describe it is it can deal with logic. I'll give you an example. Okay, this is really cool. So let's just say that somebody takes the family tree of The Simpsons, as in the cartoon, right? Take the entire family tree, And you can now write a Prologue program with some clauses, okay? We'll call those clauses or sentences. So you can basically ask, is this character that character's fifth cousin 2 removed? Or find all the fifth cousins of Bart Simpson, and so on and so forth. So that's what Prologue can do, but it's based on predicate calculus, which is one step on top of propositional logic.
Are there weak AI totally obsolete at this point, or are they changed?
I think they are not. I think weak AI is not obsolete because which calculator is powered by a neural net? So that pretty much answers the question. Weak AI is still not dead. I would say strong AI is trying to have computers to imitate how people do things. For the most part, not entirely, but for the most part, it is. Whereas weak AI is look at something that needs to be done, and then we ask, how do we get a computer to do it, regardless of whether that is what people do or not. It doesn't matter. We just want to get it done. Playing chess is one. Okay, playing chess is a prime example of weak AI because the way computers play chess is completely different from how a person is playing chess. But is a computer successful with chess? The answer is yes. They're very, very good at chess because we have gotten that down to a science. Okay, when it comes to programming, but it's weak AI because the program who can play chess with you cannot drive your car. Cannot do a conversation with you as a person. So that's weak AI versus strong AI. So Prologue definitely belongs to a programming language that had been, and I think still is used for weak AI applications. So don't let that word weak, make you think that weak AI is actually weak. It is just a term to basically say it is not generalized AI or generalized imitation of how we do things. It is more like an engineering way of doing things. This is a task to be done. What is the best way to utilize this to get it done? That's weak AI. Strong AI is basically asking, how do we do things? And how do we have the computer to imitate the way we do things to get it done? I don't trust me, so I think strong AI, is not necessarily a good idea. All right, so given that, okay, I just switched the screen because I do want to point out that Dijkstra's algorithm at one point in time in computer science is also seen as a topic of AI because it's finding the shortest route or the shortest path from one point to another point. So you got a map, right? You have all the numbers in terms of distances or of the amount of time to go from one point to another point, and then you ask, okay, if I'm here and I need to get over there, what is the best route? Well, at one point in time, it is seen as an AI problem to solve, and Dijkstra's algorithm can be seen, at least back in those days, as an application of weak AI. Does that sort of make sense or not? AI is not, there's no clear definition of what is AI. The best way to define it is what we wish computers could do, but they cannot yet do it. So that changes almost on a daily basis these days. Computer speech, even reading something from text, okay, was considered AI. Understanding human speech was considered AI. Pattern recognition, facial recognition was considered AI. These days, they're probably not considered AI anymore because it's commodity. It's no longer at the cutting edge of research anymore, and as a result, they're not AI. Computer playing chess was AI, not anymore. Computer playing Jeopardy was AI, probably can still be considered as AI. Have you guys watched that? No? Oh. Talk about distraction. I can distract you guys all day long. Okay, so look up Watson, the same as the assistant of Sherlock Holmes, Watson, which is from IBM, and just Jeopardy, Jeopardy. There we go. There are video clips. I can even show one of these. It's funny. Why is there no sound? Did I mute? No, I did not.
My dear Watson.
Hmm?
This is my dear Watson.
Oh, maybe I hooked up the wrong audio. Give me a second to see if I can fix that. It's quite entertaining. Watson is an IBM AI engine, and it is interesting. Oh, I forgot. Got to unpause it, right?
I remember that morning going
And
to the lab, and I was thinking, this is it. This is the last
supposed to be
Jeopardy game.
speaking, but it's not.
This is Jeopardy,
Oh, okay.
the IBM Challenge.
Here we go. Brad, if you're ready, make your first choice.
Let's take alternate meanings for 200, Alex.
Four-letter word for a vantage point or a belief. Brad.
What is a view?
Yes.
After the first clue of the game, which Brad won, I had just this horrible feeling at that moment that he was as good as everyone said he was, and he was just going to run the whole board on us.
Watson.
What is shoe?
You are right.
We actually took the lead. We were ahead of them, but then we started getting some questions wrong.
Watson.
What is leg?
No, I'm sorry, I can't accept that.
What is 1920s?
No.
What is chic?
No, sorry. Brad.
What is class?
Class, you got it. Watson.
What is Sauron?
Sauron is right, and that puts you into a tie for the lead with Brad.
The Double Jeopardy round of the first game, I thought was phenomenal.
Watson went on a tear.
Watson.
Who is Franz Liszt?
You are right.
What is violin?
Good.
Who is the church lady?
Yes. Watson.
What is narcolepsy?
Okay, I'm not sure whether you guys are getting the fact that Watson is beating the two human players by a huge margin at this point of the game. So Watson is an interesting AI engine because it's not neural net powered. So it is not it's not using neural nets. And at the time of the competition, it was disconnected from the internet entirely. So it was completely just autonomous using whatever it has stored already at that time. Okay? And it was just voice. I mean, it's not like somebody else in the back room is typing in the questions. So it's completely just based on, the Alex Trebek, who passed away. It's all based on his voice. So it's interesting. But if you look up another link, which is Watson and the Urban Dictionary, that's also entertaining because it learned how to cuss and how to use bad words just after 1 day of exposure to the Urban Dictionary. So the next day, when the researchers went back to the lab and had a conversation with Watson, they were not pleasantly surprised. They were surprised, just not pleasantly. Sorry?
I'm going to listen to that right now, actually. I've been using the Urban Dictionary, so.
Yep. It's really funny, but it does tell you, what computers can do in terms of learning and applying things that we normally can apply. I trust Watson as our next president. With Skynet as vice president, I think we are all set. Thank you. Mm-hmm. Hmm? Okay. Well, you can see that 有點咩？
我可以瞓，你咪得唔得？
我唔係冇得瞓，我只不過 defer 少少啫。
我興奮就想瞓覺，俾人拉企入嚟，我姐話我叫入嚟，我就叫門啦，開啦，開啦。記得上堂，keep on forgetting。今日嚇親好嘅，好過聽日係真係又上唔到。
你咪我提你啊，你擺落 calendar 度，我可以提你㗎。
未喺 calendar 咩？
唔知。
佢個 calendar 冇個 alert 我
喎。OK。
inner peace。放屁之後就 inner peace。
check 聽日返工個 schedule 點知？
隻眼睇唔開，眨唔開啦。
OK， 我都差唔多噶啦。你講先啦，十零分鐘到。
聽日先算啦，今日要瞓覺啦，瞓覺啦。Good night， good night。
你可以熄咗間燈噶啦，我可以唔需要用燈嘅。